Hello dear students, अब चलते हैं. Let us do a few more numerical problems. I hope by now you have watched the previous videos on work energy power, where I began with work done by a constant force and did few important numericals. Now I'm moving forward, proceeding to do how to find out work done by a variable force and what should be the approach, how to incorporate the integration sign properly, right? So this is what we learned in the previous videos, work done by a constant force. This we did before. In the previous videos, where F was a vector, displacement was a vector, since dot product is defined as the magnitude of the first, magnitude of the second, and cosine of the angle between them. And I have also explained you, depending on the value of cos theta, the work is either positive, negative, or 0. If theta is less than 90, cos 90 is positive, work done is positive. If theta is 90, work done is cos 90 0, work done is 0. That I have also explained. And if theta is greater than 90, then cos of that value is negative, so work done is negative. This is what we explained in previous videos with solved numerical problems. And in previous numerical problems, I had used this diagram, a constant force making some angle with the displacement of this mass to this side due to F cos theta. Now look, if F is not constant, what we have to do? Now, if F is not constant, if you consider a very small interval, small displacement ds, small, very small displacement. Suppose this force is changing with a distance, and if the change of distance is very small, then during that small displacement, F can be assumed to be constant. So then we have to write F dot ds. So the total work done, W, is equal to integration of F dot ds. Now, that is the component of F in the direction of ds vector, that is F cos theta dot ds. We have to integrate it. Now then I will explain what a variable force looks like in a numerical problem. Now, normally students find it to take the proper notations for the integration. If it is written as W is equal to, if you are trying to use this one, W is equal to F dot dx, that is F cos theta dx, then this force F must be, F must be given in terms of x, means the value of is x dependent. For example, if F is given as say 2x square plus 3x plus 7, means F is changing with respect to distance. If x changes, the value of F changes. Then you have to integrate F dot dx. Suppose F is given as minus 6y square plus y, means F is changing according to the different values of y. Then what notation you have to use? Then you have to take the small displacement dy, small displacement in the direction of y. So F dot dy, that is equal to F dy cos theta, integration of that. Similarly, if F is expressed as minus 2z cube, let's say minus 5z, means the force is varying along z axis like this, means for different values of z, F has different values. So F is variable. Then in the integration sign, you have to use it as F dot dz, right? Integration of F dot dz, that is F cos theta dz, integration of that. Similarly, if F is given as 2r square plus 6.5 r, here the displacement is expressed in terms of r. So F is a function of r. So F will be integrated with respect to dr, not dx, dz, dy. So that is what you have to be very careful. So W is equal to F dot dr, where dr is a small displacement in the direction of F cos theta. So F cos theta dot dr, integration of that. So this is the symbols that you have to use. Now suppose there is a force and the force is neither along x-axis. Suppose there is a force. If there is a force represented along x-axis, then it will be some combination of x with I cap. If a force is along y-axis only, then it will be some combination of some numbers and some j cap. Similarly, if the force is along z-axis to this side vertically up, it will be some combination of z only. But if there is a three-dimensional force, it will have some x component, some y component, some z component. Then you have to write that F as Fx I cap, means this is the value of the force F along x-axis, and I cap is a unit vector along x-axis. Means if the force is in space, it will have three components, one along x-axis, one along y-axis, one along z-axis. Suppose there is a force like this. This is the tip of the force vector. From here, if you drop a perpendicular on x-axis, that will give you the x component of the F, that is called Fx. And from the tip of the force, if you drop a perpendicular on y-axis, that will give you the value of the force along y-axis, and that will be represented as Fy, and j cap represents a unit vector along y-axis. Similarly, from the tip of the force, if you drop a perpendicular on z-axis, whatever amount it cuts from the z-axis, then that is represented as F of Fz, and k cap is a unit vector along z-axis. So this part is your force. This part is your force, having three components along x-axis, y-axis, and z-axis. Now, similarly, the displacement vector, if that displacement vector is neither along x-axis, nor along y-axis, nor along z-axis, somewhere in space, then that displacement vector will also have three components, one along x-axis, one along y-axis, and one along z-axis. So then what we have to write? dx I cap, dy j cap, dz k cap. Means this is the value of the displacement along x-axis. This is the component of the displacement vector along y-axis. This is the component of the displacement vector along z-axis. So this much part represents your force, and this much part represents your displacement vector. Now, since in dot product, as you already know, I dot I is a unit vector, its magnitude is 1, and this I and this I cap, they are in the same direction, that is along x-axis, so angle between them is 0. Cos of 0 is 1, 1 into 1 into 1. Similarly, j dot j, unit vector along y-axis, they are dot product. Magnitude of the first, magnitude of the second, these two are in the same direction along y-axis. So angle between them is 0, so cos 0 is 1, 1 into 1 is equal to 1. Similarly, k dot k is also 1. Now, if you take I dot j, magnitude 1, magnitude of this is 1, along x-axis, this is along y-axis, cos 90 is 0, so this whole thing is 0, right? Similarly, if you take I dot k, that also becomes 0, because angle between I cap and j cap, I cap is a unit vector along x-axis, k cap is a unit vector along z-axis, so they are perpendicular, cos 90 is 0, so I dot k is 0. Similarly, j dot k is also 0. This you already know in your school days. So now let us apply that. fx I cap dot dx I cap. Fx dot dx. This fx, this dx, they are in the same direction. I dot I is 1. So fx dx. Integration of this from the initial position xi to the final position xf. Now, similarly, the dot product of fxi cap with this will be 0 because I dot j is 0. Similarly, the dot product of fxi cap with this will be 0 because I cap dot k cap is 0. Means fx I cap only remains with this, giving you fx dx. And the value of this integral within the limit from initial position to final position xi to xf. Similarly, if you take the dot product of this with these three terms, only fyj cap will remain with dyj cap. Fyj cap with this will give you 0, fyj cap with this will give you 0 because j dot I is 0 and j dot k is 0. So we get fy dy, j dot j is 1. So 1 into fy dy is fy dy, its value from y initial to y final. Now similarly, fzk cap will remain with this only. The dot product of this term with this as well as this will be 0 because k dot I is 0, k dot j is 0. So fz k cap dot dz k cap dot k cap is 1. So we are left with fz dz, its value from z initial to z final. So this expression will therefore use, this expression we shall therefore use for finding out work done in case of a variable force. So now let us do a problem. Let us do a numerical problem and proceed further in next videos for higher order problems. So what is the conclusion? For variable force, your work done is equal to f dot ds. Its integration, that is dot product has a cos term, so f cos theta ds, right? So this will be used for doing work done in case of a variable force. Now look at the numerical problem. There is a force given as F is equal to 4x I cap plus 3y square j cap Newton. This force is acting on a body and the body moves from this position to this position. This is a three-dimensional position, this is a three-dimensional position. It will be difficult to show you in a two-dimensional page, but still I will explain you. Now first let us find out how this force is a variable force. So let me first explain in a different page. The same question is here. Now I have drawn two coordinate axes given as f is equal to 4x I cap plus 3y square j cap. Now let us take some values of x and y. Suppose x is equal to 0 and y is equal to 0. So this whole terms becomes 0, this becomes 0, so force is 0. Now if you change this value of x and y, the f will change. Let's say x is equal to 1 and y is equal to 1. So this force becomes, let me show it here. X is 1. 1 into 4, 4. 4 I cap. Y is 1. Put y is 1. Square of 1 is 1. 1 into is 3 plus 3 j cap. Then where is this force? Where the value of x is 1 and y is 1. 4 units along x-axis and 3 units along y-axis. I have taken 1 centimeter, 1 centimeter, 1 centimeter, 1 centimeter as units for this side. Similarly to this side also I have taken 1 centimeter, 1 centimeter, 1 centimeter, 1 centimeter as units. So for x is equal to 1, y is equal to 1, this force F should be represented 4 units, 1, 2, 3, 4, then 3 units, 1, 2, 3. So where do I arrive? I arrive here. Means this is the force. This is the force. Now, if x is equal to 1 and y is equal to 1, this is the force. Let it be F1. Now let us change the value of x and y again. You can change value of x and y together. You can change the value of x only, keep y constant. Let's say x is equal to 1 and y is equal to 2. Then how this force should look like? Then the force should look like, for x is equal to 1, it is 4i cap. For y is equal to 2, 2 2s are 4, 4 3s are 12, plus 12 j cap, plus 12 j cap. So 4 units to this side, 1, 2, 3, 4, and 12 units to this side. So 12 units to this side means the force will be something like this. 12 units. 1, 2, 3, 4, 5, 6, 7, 8, 9. Suppose it is here. So the force vector will be like this. So what is the conclusion? So let it be F2. Let it be, for this value of x and y, let the force is F2. Now if you look at, if you change the value of x and y, the force is also changing in the direction and also the magnitude. The magnitude of this F1 is less, the magnitude of this F2 is more. Let us change only one of them. Let us say y is equal to 1 and x is equal to 2. Then your f, let it be F3. If you put x is equal to 2, 2 4s are 8, 8i cap, and y is equal to 1. Y is equal to 1. 1 into 1, 1, 1 into 3, 3, plus 3 j cap. So the force will be having 8 units along x-axis, 1, 2, 3, 4, 5, 6, 7, 8, and 3 units along y-axis, 1, 2, 3. So it will be, so the force will be this. So what is the conclusion? So the conclusion is such an expression, if some combination of x and y, it can be some combination of x only, or it can be some combination of y only, or it can be some combination of x, y and z, then the force is variable. So also the direction is changing, the magnitude is changing. Therefore, we have to use the integration process to find out the work done, right? Now, then coming back to the position, this position. Where is this position? X value, y value, z value. 1 unit to this side, 2 units to this side, then minus 1 unit along negative z axis, means from this point, 2 units to this side, 1 unit to this side, 2 units to this side, and from this point vertically downward 1 unit. That will be the tip of this position vector. Similarly, this one, 4 units, 4 meter along x-axis, 5 meter along y-axis, 7 meter along y-axis. So that position will not lie on the plane of the paper. 4 units to this side. Let us now change the units because I have less space here. Let's say 1, 2, 3, 4. Then 5 units to this side. 1, 2, 3, 4, 5. Then 7 units from this point vertically upward along negative z axis is the tip of this position vector. So clear about how this force is a variable force and where are these two, where is this point and this point in space. Now then let us then go back to solving the problem. Solving the problem is easy. So I have already explained you how W is equal to fx dx from initial position to final position, fy dy from initial position to final position, fz dz from initial position to the final position. So in this numerical problem, therefore the work done will be equal to integration of fx dx, Now, from which position to which position? Now I am only integrating the x value, that is from 1 meter to 4 meter. So it will be from 1 to 4, right? Then plus integration of fy dy. Now that is due to the y value of the force and the limit of y. This is the y value, initial position, this is the final position, that is from 2 to 5. 2 to 5, right? Now then coming back to f z dz. Now there is no z component of this force. This is not there. Now even if there is a limit from -1 to 7, this part will be 0 because this is 0. Fz, there is no component of this force along z axis. So this part becomes therefore equal to 0. So this part therefore becomes equal to 0. So from 1 to 4, fx, that is equal to 4x, its value only, that is equal to 4x dx. Now you might be wondering where this I vanished, because I just explained when you took the dot product of fx I cap with dx I cap, fx I cap, dx I cap, I dot I1, so fx dx. So we are left with only fx dx. There is no I cap here. Similarly, if you take, then you might say there was a j cap here. Why it is not there? This is what I explained you before. If you take the dot product of fy j cap with dy j cap dot j cap is 1. So we are just left with fy dy. So we are just left with fy dy. There is no j cap here. Dot product is already taken. So plus from 2 to 5 and fy is equal to 3y square. 3y square dy. That's all. And this part is equal to 0. That is what I explained. Now 4 comes out being constant. So integration of x dx from 1 to 4 plus this 3 comes out, integration of y square dy from 2 to 5 is your total work done. And now it is simple. Integration of x with respect to dx is x square over 2, its value within the limit from 1 to 4. Now 3 is here. The power will increase by 1. So 2 plus, let us write it, 3 by 3, its value from 2 to 5. So, so this is the variable. So 4 comes here, square of 4, 16 over 2 minus, if you put 1 here, 1 square 1 minus 1 over 2 plus 3 times, if you put 5 here, 5 cube, 5 into 5 into 5 is 125 over 3 minus, if you put 2 here, 2 to the power 3, that is equal to 8 over 3. So this becomes 4 times 16 minus 1, 15 by 2 plus 3 times 125 minus 8. 125 minus 8 is equal to 117. That is equal to 117 over 3. Now this 3 cancels with this, these 2 cancel with giving us 2. 15 2s are 30 plus 117, so that is equal to 147. So that is equal to 147. Since the force was given in Newton and the displacement, the position vectors were given in meter, so work done is equal to 147 joules. Okay. So I hope it is clear to you. Then we'll slowly move on to little more difficult problems. Then finally we'll arrive at solving numerical problems using work energy theorem. So that's all about. Thank you.